without further delay, let's begin the session with Bismillah. Okay, Pak Latif, you can have the stage now.
Thank you. Thank you. Assalamualaikum warahmatullah and very good morning to everyone. So my name is Pak Latif. So I think we're going to have very interesting topic for today, origin of hydrocarbon. So hydrocarbon means that it's like hydrogen and plus carbon. So that's why they call it hydrocarbon, hydrogen and carbon. So H and the C, for that formula lah they call it. Okay, so yeah, this is the title. We have introduction, origin of the natural gas, the crude oil, and the supply and delivery of the crude oil, and then we start to explore, how the hydrocarbon be generated, the history of hydrocarbon migration and accumulation, and then we try to see what are the reservoir rock, which is the sedimentary rock in our case. The most cases going to be in sedimentary rock. So we're going to share with you the sedimentary rock properties, the environment, the basin, and so on. And then, of course, we take the opportunity try to understand what are the products being produced by hydrocarbon. So you can see that every day in our life we are surrounded by hydrocarbon, the petroleum products, especially plastic lah. It's all coming from the petroleum. And then we try to cover also any industry related to hydrocarbon. So just to show you how big is the market for hydrocarbon, and that's why we're interested to know all these particular relationship between the origin and then the generation of hydrocarbon and the use of the hydrocarbon products. Okay, let's start with the first subject. Before, just to give you some idea about myself, so your cikgu, whatever. So actually, I've been working about almost like 38 years in oil and gas, retired. So when I joined Petronas or even some of the company, they will try to put a title for me. They call it subject master expert in well and drilling engineering. So I have a degree from UTM, and I ascended some master program lah in Hyderabad. So key assignment, as you know, I've been working with as a senior engineer, working from the bottom, doing the planning and a lot of things, the various complexity of wells, and in Gulf of Thailand, and then in Saudi Arabia, 5 years in Saudi, and of course, for Gulf of Thailand operation, Malaysian Thai Joint Authority area, I spent about almost like 8 to 9 years, and then of course. With those as engineer, I have the opportunity to really have the hands-on, direct hands-on, or doing the jobs on the rig, doing the planning, execution, and even do some suggestion, evaluation, risk assessment, and so on. So many assignments have been gone through. So I'm a bit lucky to have the opportunity, to learn the business from A to Z. Okay. So at the same time, as you know that the expertise that I can cover is quite mostly about oil and gas. So from the high pressure, high temperature exploration drilling, development drilling, well services, well repair, well intervention, and of course I saw you involved with the extended reach drilling (ERD), and at the same time also doing involved with the planning of HPHT. I'm actually one of the members of reviewing most of the program by engineers before we implement. And I have opportunity really to get involved with the review and understanding about the deep water exploration campaign. Carbonate drilling is really popular in Saudi Arabia, as well as now coming up to Sabah Sarawak, carbonate drilling. At the same time, well P&A, well plug environment is another subject that seems to be popular nowadays. And you can see that I've get involved with well P&A for quite some times, and especially when I was with Charigali Shell in Baram Delta, we have a 3 years campaign to really do the well plug environment. Okay, so that's about myself. Very long, 38 years, you can see.
Sorry, tidak ya.
Adjustment. Okay. Share document. Hmm. Okay. So I think for introduction, we start with what is hydrocarbon, and let me see how to remove this. Yeah? I mean, just let me remove the top one just alone. Yeah. Okay. So before that, we say there's anything in the top. Huh? Okay. So what is hydrocarbon? So hydrocarbon, like we know, is going to be a combination of hydrogen and carbon. Uh, So we can see that for ethane, this is two carbon element and six hydrogen element. So we could put a drawing, it's going to be like the two C and then the six hydrogen around it. So for ethane, it's much more stronger, much more heavier. So you have more same carbon, but going to should be sorry, it's going to be less hydrogen, so it could be lighter than ethane. Sorry, this should be methane. Sorry, I think there should be methane here and then ethane here. So you can see that's the difference. Okay, now hydrocarbon is class of hydrogonic compound composed of hydrogen and carbon component. And of course, hydrocarbon usually form a straight change, so it has become very strong and can be linked to one another. That's why for hydrocarbon, they can be converted to plastic because they can have a long chain. And plastic normally we're talking about the long chain of of this component bonded together. Okay, I think that's the basic understanding about hydrocarbon. Of course, at the same time, people are asking about hydrocarbons. So I think this coming from the Latin words. They call it petra, petroleum. So petra is the rock, and oleobium is the oil. So that's always be the petroleum actually coming from the Latin, because normally most people in the world they've been using Latin as their reference, and then of course even the American, in the Europe, I think Latin become very the basic language to really come up with some term because most of these old people they use Latin since they can communicate from one another with different dialect with some Latin as their basic words in their discussion or even in their communication. So petroleum is rock and oil. Okay. Then it's quite interesting to see how the hydrocarbon element will be. So sometimes also being caught by surprise to know that Canada has such a huge tar sand, and they have been producing from the tar sand equivalent to 40,000 barrel a day equivalent. So that's if we're talking about mining, not drilling away. This is mining because tar is very semi-solid, so they have to really mine. And you can see that from this drawing, the tar itself actually being embedded for too deep into the well, into the formation, into the earth. So they've been using steam to really heat up the tar to make it liquid, and then they extract from the well, which is about far deep. But some of this tar sand actually coming up to surface, that is where they start to do the mining. For example, if the tar is about 100 feet or 100 meter below the ground, so they start to dig and start to touch the base of the tar sand and try to mine. I think I have the drawings of this. You can see this how the tar soil, tar oil in or the in Canada, they have been mining this using all the big lorries, the big trucks, huge excavator, and then they will have the refinery that will process the sand and extract the oil from the sand. So this is going to almost quite a big industry. It's about 40 to 50,000 barrels a day, which is huge, compared to we produce offshore or onshore. But this is from we call it from really digging up, and for the mining of the sand. It's unique area. I think we have mostly Canada have this big zone, and then we have also Venezuela and some other area that have that tar sand. So now we go to Malaysian side. So from the drawing here, we try to see the hydrocarbon area. So from the map here, you can see that we have the Malaysian Peninsula Malaysia, and we have all the offshore oil and gas, which is quite far away. I think the nearest is about 50 kilometers, and then the furthest from Terengganu itself is about 300 kilometers away. So we have mostly offshore, nothing much near the shore for the Peninsula Malaysia. So mostly the oil and gas. You can see that some of the color here, some dark color is referring to oil field, and some lighter, normally it's a gas field. So it's more or less we can see. So the gas field and the oil field color. And I've been working mostly in I think my last in year 2000 I'm working with this is this area Malaysian Thai area in 2000 I think 2010 and 2015 and I'm working in this area Malaysian Thai joint activity, and JDA is where I'm spending about almost 8 to 9 years doing the gas drilling around this area. Okay, when we go to Sabah and Sarawak, you can see we have another field, but in Sabah and Sarawak, I think you can see that most of the oil field is getting closer to the shore, especially when I work with Baram Delta, I think it's very close to the shore. Even at the beach along the Miri side, we can see some of the platform, especially when you are in Bintulu. Some of the area is very clear to see some of the platform nearby. And of course, Miri is much closer lah. And at the same time, you can see that in Brunei, also it's close to Miri, close to Sarawak. Brunei is independent country. They have a huge oil just between their neighborhood area. And even in Brunei, they have onshore wells, onshore drilling. And you know the history of Miri. Miri have a lot of onshore wells. I think Shell been doing that during the Japanese occupation. They use the oil to be refined for for their truck, for their their quality or the machine military machine. And Miri, or even in the town of Miri, there's about 120 wells being drilled before, shallow wells. And then that's the history that we have mostly first oil in Malaysia from Miri side. So and then the extension of those reservoir is going offshore. We have all those Ferry Baram and then all those berry fields and so on in Sabah Sarawak. Of course, now we can see that most of our oil actually being explored in the deep water. So Mopi have their big kakap. Bumusuk kakap is shell area. And then, of course, some of the deep water from Sabah also is coming in, with mostly gas wells. So we can see that most of our oil and hydrocarbon extraction in Peninsular Malaysia and in Sabah, it almost come to the almost a mature stage. I think we have discovered most of the oil. So now I think we are exploring more on gas in Sabah and Sarawak. So that's the history of hydrocarbon in Malaysia or discovery in Malaysia. Okay, the next one is what is natural gas. And then, of course, natural gas is something that talking about a gas that we have been using. As you know, hydrocarbon, we try to we split into two category. One is gas, one is oil. So for gas, you can see that now we have the methane, which is one C, and then the 4H combination is bonded together, and this structure means that it's a very light element. Air is much combination because air we have nitrogen, we have carbon dioxide, and then we have all the other component in the air. So for gas, is the clean gas is methane, only one carbon and the 4H. And of course we have ethane. We have two carbon and then 6H. That's much heavier, much more stronger. So in terms of the burning power, of course the methane have a much more burning power compared to ethane. But in terms of the liquidity and mobility, volatility, normally methane evaporate faster than this ethane. Okay, the propane have more. They have 3 carbon and 8 hydrogen. Eight hydrogen. Butane is much more. It's almost like going to liquid. Butane. Methane, ethane, and propane mostly in gaseous form. Once you go to C4, component, then it could start become a liquid a bit. So that's how we see that gas is going to be more or less in the situation of simple gas with one C, or even to the complex C plus plus, to make it more lighter, even up to liquid liquid form. Okay, let's go to the percentage of the gas itself. For example, for natural gas, you mix up you analyze the natural gas. Normally, the common natural gas, you have about 90% of methane, or let's say 80% in the middle, average 80%. So among the 80% of the gas itself, of course, the other component will be carbon dioxide and then the hydrogen sulfate and so on. But the rest is very small. But I think what is common for the methane composition is the carbon dioxide, and then as well as the H2S and so on. So these two elements here decide the remaining components of methane. In Malaysia, in Sabah and Sarawak, we have discovered gas, and most of our gas actually consists of about 20% of CO2. So you have 20% CO2, so actually your methane is left only about 80%. In the Natuna Island, we have CO2 up to 60%. So if CO2 is 60%, your methane is only about 40% of that volume. So you have, say, 100 barrel of gas. If the CO2 is 60%, then you have 60 equivalent barrel of carbon dioxide, and other 40 barrel is on methane. So carbon dioxide decide the total effective volume or the commercial volume of a gas. So a gas, like I mentioned, consists of those elements, and the key targeted gas composition is methane. So we have high CO2, your methane will be reduced. So unlikely for us, we have a big field in Sabah and Sarawak, and then it will be decided by the carbon content CO2. How much CO2 will be in that crude, that we decide the commercial value of that gas. So what we should do once we have the gas coming up from the earth, from the ground, we have to really remove the CO2. So if 100 barrels or 100, let's say 100 barrels coming up from the ground, and then 40% is CO2, then it's only 60% left for the methane. And plus, of course, you have to reduce the other component, the small component, if any. So this is how we value the commercial aspect of the gas is based on the content of CO2, you know. Okay, and then of course for hydrocarbon natural gas, you have consists of all those elements. That benzene actually is something to go a bit on the liquid side. You can see all the composition of benzene going through all the different usage of benzene to the industry. You can use for solvent, you can use for nylon, and then you can use for plastic and so on. So it's starting point, and then of course to make it benzene, we can really even process the methane and break it down and make it combination up to benzene before it can be used for a multiple usage. From the simple gas, you come to the much heavier gas, benzene, then the other products will come in. But it's much more stable, because methane, which is very light, is very volatile, very aggressive. So we want to make it much more stable. So benzene is a starting point to start making all the other products, because it is less volatile, less aggressive in terms of the ability to put on fire, to be on fire and so on, or flash point, we call it. Okay, so let's review again about natural gas contaminants. I think we know about natural gas coming up from the ground. It consists of other components. Some component is considered contaminants, like CO2 is considered contaminant. CO2 is very corrosive, so that's why you can start to attack some of the piping that carry all those things. So if they have contain no hydrocarbon, then it's sweet gas. So what we call it here is only if you have even has CO2 but no hydrocarbon, it's called sweet gas. And sour gas is something when you have H2S exceeding, let's say, I think about 0.5% even, it can consider sour gas. It's very corrosive. It is dissolved in oil and in gas, it still be okay. But once it becomes free hydrogen sulfate, it start to attack your metal. It will cause a total failure, immediate failure of the metal, which is in the free form. So this is dangerous component of our contaminant called hydrogen sulfide or H2S. Even in our industry, for example, you are going to a hole, maybe something like a pit, whatever, very deep down, like the coal mine. The coal mine sometimes have H2S, and then the concentration might be quite high to a certain area, and most workers will be dying because of they breathe in the hydrogen sulfide. And within, I think if the concentration is more than 2% or 3%, within 10 seconds, yeah, you're going to fall out, and then your brain will be most damaged by H2S. So it's very risky, H2S. So I think mostly dry gas talking about the liquid content lah. Kalau any gas will have some element of water, percentage of water. So methane is considered a dry gas with the condition of you might be having less than 0.1 gallon per thousand cubic feet of liquid. So this is a scale. Then we're talking about M means thousand, double M is million. So that it does not M does not mean million unless you put in here MIL, a million cubic feet, then it's going to be million. But if it is only one M, means thousand. Double M is million, and triple M is going to be billion. So a kind of analogy, yeah. Okay, wet gas contain more than 3% of liquid. So ethane, methane are example of wet gas because it contains some of the liquid vapor that make it also stable, much more stable compared to our methane. So in summary, sweet gas, no hydrocarbon, no H2S, sour gas, beach H2S, dry gas with less water content, wet gas is more water content. That's more or less the summary. Okay. Let me see. Any question that you have, you can just put in the chat room. Then we'll be try to answer that question. Good measurement. This is quite interesting that when we talk about gas, if it is liquid, always we like you go to the petrol station, you go and try to pump your petrol, or I think in UK, in US they call it gas, password. So for you go to petrol station, they will be putting in liter. So 1 liter, the cost is about $2.05 for the normal, RON 75. So now, of course, the gas measured in cubic meter. And 1 cubic meter, of course, is equivalent to 1,000 liter or 35 feet squared. So because gas always occupy a big volume, that's why we measure in meter cube. And of course, in most of the production offshore, we always refer to million cubic scarf, so MCF. So you can say the MCF is 1,000 milliscarf. So if this 1,000 is clearly the million cubic foot that we're talking about. So go back to the measurement. So 1 BCF is going to be 1,000 million, 1,000 million cubic foot. And that's about the number lah. So it's quite 1 billion cubic foot. It's considered like for the reservoir calculation, then you use the big number. But of course for production, it's going to be the MMCF number. So now, always in our comparison, we try to compare with oil. So we try to understand in terms of the we call it the burning capability, the burning power of the gas versus oil. Then we try to use the combination of that volume. So in terms of the volume that we normally use is that 1 barrel for oil equivalent the power of the burning power is the BTU for oil and gas to be equivalent to this number is about 6.1 thousand cubic feet. So it is 1,000 cubic feet. So 1 barrel is about 6,000 cubic feet. Something like that. In terms of the burning power, the thermal value, the thermal value. So if 1 TCF of reservoir, then it's equivalent to 160 million barrel. So that's more or less to understand how big. So in oil and gas, if you have anything above 50 million, it's going to be quite a good reserve. And if it is offshore and close to the shore, the 50 million will be much more economical to develop. So for offshore, maybe about 100 kilometers away because of the pipeline requirement. And of course, you need to have more than 100 million barrel to make it economical to develop a field. So this is, if it is 100, means that you need 1 TCF of gas to be able to really put it on production and then make it economical to produce. So that's more or less some guideline KPI for the value and the economics of the potential project coming in. Okay, 1 TCF is a good number lah. So the next one, natural gas. Normally, what happens actually, you have talking about the underground. The underground itself is sometimes you go to 3 kilometers below the surface, the seabed. Sometimes can go up to 5 kilometers. Some wells, like deep water. I mean, talking about the area of Sabah and Sarawak, where we have a situation of deep HPHT wells. So the well can go to almost like 4 kilometers to 5 kilometers before you reach the big reserve of gas. So in terms of the gas itself, as you know, even like in a crude, you have a crude because of the high temperature and pressure. Based on the drawing here, you can see that this is the bubble point, means that everything above here is gas and everything below here is liquid. So what happens is going to be in the middle here is a 25% liquid here. I mean, it's going to be a gas, 75% gas in this region. So the temperature, pressure, when the pressure become more and more, you can see that the percentage of liquid is going to be getting less. So going to be more gas in certain area. But of course, you can see that the percentage of liquid, it depends on, as we go and high temperature, mostly everything will be more in a gaseous form. And that's what it being shown in this graph lah. So when we produce oil, for example, normally the gas will dissolve in that oil. So once it comes to a certain depth where the pressure, the bubble point pressure or the flash point pressure is being reached or lower pressure, then the gas start to be released from the crude oil. So you can see how even though crude oil, they have still some gas, but in some well we have a dry gas reservoir. Of course, the dry gas will come into surface directly as it is, and then the slight of compression. For example, if it is 1 million at the bottom, and then we coming up is about 950 million pound, maybe just but less, about 5% compressibility. So that's how the gas dissolve in the mud, in the crude oil, and go to surface and it release. So you have gas and oil production at the top. So okay, and of course for the natural gas, as you know, in the reservoir condition, when we have the oil being trapped, maybe 3 kilometers down in the earth, or 5 kilometers, you can see that some of the oil is still intact. Gas sometimes is being dissolved, so remaining free gas will be at the top. So because as you know, if you understand the nature of the light, I mean how heavy is that? So water is heavy, so it's going to be after million of years, the water will be more or less segregated downwards, and then oil will be separated to make it in the middle, and the extra free gas will be at the top. And of course, it is the high temperature, high pressure, most of the gas can be also inside the oil here. So you don't see any more gas. But when you produce, the dissolved gas will start to come up to surface. But in this case, there's a free gas. You have a three element, water, oil, and gas. Because of the density difference, that's why they have been segregated. They're separated millions of years ago. And once we touch, then we produce the oil itself. Okay. So some other area they have some different trap, and of course this sometimes you have all the gas itself and the water is pushing up. So the water system here actually provide additional energy to push the gas. When we produce the gas, when we produce the oil, what happen? We are going to deplete the pressure because we are sucking, we're creating a vacuum effect in the reservoir. So the reservoir pressure start to get less, but since the water volume is big, coming from a big reservoir, the water system, the power from the power to try to push the reservoir into call it a stable pressure, and the production will be much more stable over time. So that's the advantage if we have a water drive system. But if the water drive system is very weak, then once you produce to certain volume, the creation of vacuum try to actually deplete the reservoir here, and then some to a level where there's not enough energy for the oil to be we call it naturally flow to surface. That is where you need artificial lift, gas lift or pump, downhole pump to really try to suck the oil because of the depletion that happened. Okay. So the next one, actually, we can now go to the crude oil. To the gas, we have covered gas, understanding about gas that actually dissolve in the oil, and sometimes it's a dry gas. It's going to be produced to surface, and if it is produced too much, the vacuum effect will be there, and then of course you need to have a drive or artificial lift to make sure you continue to produce the hydrocarbon. So now we come to crude oil. So for crude oil, I think, yeah, as you know, it's quite understandable. We have seen that a lot because normally we can see at surface, even like minyak hitam, or the black oil, the engine oil, is all just similar to the properties of the crude oil. But in our industry, we can see that crude oil actually become defined to various categories, different viscosity, and so on. So for crude oil, coming up from a complex mixture of the carbon, so it's quite a big range of crude oil. So crude oil is a member of paraffin, naphthalene, and aromatic aspartic series. So there's a category, you have so many categories of that, and it's a liquid at room temperature and pressure. I think we have seen the graph itself. When it is normal pressure, like room temperature now, this liquid oil will become a liquid. But once you pass it, when you go, when it's in original location and down 3 kilometers down the earth, of course, this crude oil can be in the various form. It can be even in gas form in certain cases because of the reaction of the component itself. And then, of course, some of the gas will become a condensate and so on. So crude oil contains about 80 to 37% of carbon and very small percentage of hydrocarbon. So it's more carbon than hydrogen. So the remaining can be all the other like sulfur, nitrogen, or oxygen in the crude oil. So, but still, the burning power is still there. If you have more of the hydrocarbon, let's say you have the carbon of about 10%, it have giving you such the thermal value. You can create some the combustion value by itself. Okay, so product made from barrel of crude oil. So we have a crude oil coming up from the offshore. We can start to break down the crude oil through the refinery. It can become diesel, jet fuel, and then we have the residue of heavy oil, and then you can also have some gas inside that, liquid petroleum gas, and of course some gas coming up from the when we dissolve in the gas and coming up into free gas, it become a gasoline or gas form lah. So you can see 1 barrel of oil give you a multiple products from diesel, jet fuel, even the gasoline, and then even for heavy crude oil, and even so some of the heavy crude coming up from Kuwait, for example, the byproduct can be tar that can be used for our road construction lah. There's some of the heavy crude coming from Kuwait that we only import this heavy crude just because of the requirement for us to have tar for our road construction. Okay. So the measurement of crude oil, like before, we have mostly we measure in liter, but as SI unit, normally they will refer to meter cube, meter cube. So 1 barrel is about 159 liter. So we have been talking about barrel. So for oil field, like I mentioned to you, 50 million barrel is a reserve, recovery reserve they consider economics to do for simple project near shore. But if it's far from the offshore, we need at least 100 million barrel to make it economical to develop the field. So that's about the more some comparison about FDP potential economics for available. Okay, and then we come to the supply and delivery of crude oil. Of course, when we extract the oil, we want to understand how we deliver the crude oil to the market. Okay, so you can see that from the drawings here. We have the fruit oil that is processed, and then we have the kerosene, we have the jet fuel, they have diesel, and of course now for fuel oil, we have the range of different composition based on the burning power. For example, some of the so the sport car they need a special petrol to have much more power, burning power, much more thermal combustion requirement for the sport car. So a different process can be done process in the refinery by adding chemicals and further processing. It becomes a different value for the fuel oil. So we start from the oil from here from the ground, and then this of course we can extract with the various style, whether it's going to be like donkey, and then we have the palm and so on, or natural flow, and we pass all the oil to the refinery. The refinery and chemical plant means that they are adding in some chemical, but well, you're surprised that even from the hydrocarbon itself, all the contaminants like sulfur and some other elements can be also become chemical plant. Even some of the gas itself can be converted into fertilizer and so on. So once you have refined the products, then you go to the feedstock on the manufacturing companies. Some will be using some of the gas for power plant. Some will be using the gas for fertilizer. Some will be using for we call it for detergent or gum. And so many products that can be produced from this refinery based on the requirement by the customer, and then it will be delivered to the store for selling if it is gas in tank or in bottles, or maybe some plastics and so on. It's all going to go to for the market lah, for market. Okay, now even refinery can see that it can go to all the storage where you can have the fuel or diesel or petrol for export or even for distribution to the customer. And some of the fuel will go into the jet fuel for jet fighters, for aeroplane and so on, helicopters. And some of the products also coming in, we're going to go for, of course, our house for gas, and then our petrol station itself for diesel and for petrol. So this is the distribution delivery of the food product from well to refinery, from the plant itself, and then you can also go to the storage. On the storage shelf, we deliver to the customer even through pipeline or through trucking, using truck to the house and even to the petrol station. Okay, so that's how the supply and delivery of fuel oil. So now, actually, because oil have so much variation, we try to understand how we differentiate them. So when we produce the oil from offshore, each storage vessel, floating storage FPSO, will have certain quantity. For example, field A, the group of field A actually coming through one floating storage, and then the API is certain amount, and all the quality of the crude will be more mainly mentioned about what percentage of lead, what percentage of CO2 and so on. So the API is calculated based on this formula. So you can see that this is standard formula by API and specific gravity in SG. So for example, if the oil specific gravity at room temperature is 0.95, which is lighter than water, then the API will be about 17 degrees. So it's quite heavy, quite heavy. It's like our engine oil, more or less. If it is condensate is very light. It's just a gas being processed or being converted to liquid at at normal temperature, or 0.8, which is diesel about 0.79, very close to diesel. So the gravity of this condensate is about 45. This is about diesel lah. Condensate will be coming up to 50 degrees API. So this is more or less some calculation to show you how the API decide in the viscosity. The higher the API, the lighter the oil. So it's a bit reverse. So the lower the API, the thicker the oil will be. Okay. See some example like you can see light oil 45, condensate about 50, like I mentioned. Medium oil is 20 to 31. So in our production in Peninsular Malaysia, we have a Tapis blend coming from mostly ExxonMobil area, Tapis, Guntung, and so on. What happened? The API is about 40 for the light. It's very light, the high quality oil from Tapis blend in Peninsular Malaysia, and we can sell that at a premium. For example, if the oil price is $70 per barrel, we can sell the Tapis blend at about 75 for $5 premium because of the high quality, less lead, and then very low CO2. So that's why I have a higher value lah. So if the field have more contaminants, like for example, some another field in Peninsula or in Sabah have a API of 30, then of course the commercial value will be less. And if you have more CO2, for example, customer will request CO2 of about less than 5%. So if less than 5%, then you have to process, and only with the 5% CO2 you can sell to I mean to the market lah. Otherwise, you have to reprocess again. So heavy oil mostly very is less than 22. Huh? Okay, that's how we look at it. So there's a table about bitumen very hard about 5. So 5 API means like a tar. This is a light tar. So 5. And like you mentioned, diesel it will in the range of about 35 to 40 lah, the diesel itself, or petrol. And 45 getting close to condensate, much lighter lah, condensate. Okay, so I think we are okay now. So I think we can still open for question. If there's any question before we have a short break.
Hello.
All right, we have a question from Fahmi.
Yes. Okay. Circling back to the from the extraction part where you mentioned that most of the oils they have sulfurs. I mean, whether it be not too many or maybe we have like small amount, but concerning about the sulfur, how do we deal with the sulfur? Do we really extract out of the sulfur immediately upon extraction from the well, or do we extract them at the refinery plant?
Yeah, of course. I think what happened, lead itself actually have some effect on metal. So the higher the lead content, the more you'll be more attacking the integrity of the casing. So if we have a plan, for example, to have, for example, the pipeline has been designed to accept 2% of lead, for example, then you can still have, for example, the lead coming up from the ground is about 5%, so you have to reduce to 2%. So you need a plant to process that. So the processing platform, we have the sulfur removal unit. If the lead, for example, is less than 2%, and then they can still continue. There's no need for a sulfur facilities, but they can just pump through the pipeline to shore, and the shore will start to take off the remaining crude based on the customer. If the customer say they need only less than 0.5%, then the next step is to process that 0.5%. But normally the pipeline we should be able to accept a bit higher because we try to avoid having the sulfur processing plant offshore because you need another structure to support that facility. So it's based on where we are, how much acceptable, how much we can pump to the pipeline, and then of course when we go to the receiving point on shore, they can have another stage of processing where they can reduce further to meet the market demand.
Okay, I see. Interesting take. But I have like another question that pop up from the like let's say you are mentioning if you need to reduce down the sulfur unit to 2% by introducing the sulfur removal unit on the extraction platform, right?
Yes.
So, how do you remove those sulfur from sulfur removal unit? Do you transport them back by pipeline, or do you have any other ways that you discarded those extracted sulfur from the oil that we extract from the well?
Yeah. So I think the question more on the byproducts. So when we process the sulfur, it's going to be like almost like a semi-liquid, like a paste. So what we do is that because we know that sulfur will also react some of the so it is sulfur. This is not lead, sulfur. So sulfur normally is quite friendly in terms of processing. Uh, I think we're talking about lead, not sulfur, lead. Okay. I think for lead itself, you process, it's going to be like a semi-solid. Since you're going to attack metal, normally we have a special container with the plastic lining to really storage that. Then we put in certain packages, and we're going to load all that into supply vessel and going back to onshore for disposal. So there'll be an industry demand for lead actually, yeah. That's why I think sometimes they have some value itself when we sending back to offshore. But if there's no taker, no buyer because of the quality of lead, then of course we have to discharge to the approved disposal area. Like Negeri Sembilan, there's one area where we can dispose some of this special lead or some of the contaminants from something like small quality of radioactive. There's an area in Negeri Sembilan that can accept that disposal. So lead, Fahmi, not the sulfur.
Probably Fahmi's question is actually
Yeah.
what we call as uh for
Sulfur.
hydrogen sulfide.
Yeah, I was concerning
Oh,
about the hydrogen
Yeah,
sulfide.
hydrogen
oh yeah,
sulfide. So
understand.
if
Yeah,
hydrogen
But
sulfide, it
interesting
would be a
sharing
bit
on lead as
different.
well.
yeah,
Yeah,
right. I think.
if we're talking about lead, that's what Pak Tip was mentioning just now. But if
Yes,
we are
yes.
talking about hydrogen sulfide, then
Mm.
it's a different method. During drilling, you probably will add
Zinc
the
carbonate.
zinc carbonate, or what we call as sulfide scavenger. The scavenger. So we chase away the sulfur elements over there. And then during production, we have what we call as sweetening process. So that is a different process altogether lah. All
Yeah.
right. Thank you.
Okay,
Yeah, I
okay.
think you're
Thank
right,
you.
Fan, because for H2S it's so dangerous, it cannot be free. If it's a free gas, it start to attack metal. So that's why before it's coming to offshore, even the processing itself, we try to make it dissolve with some chemical reaction by adding in additive like zinc carbonate will absorb H2S, convert it into a powder. So we don't see any free H2S because of that chemical reaction.
Okay, okay. Interesting
Mhm.
no,
Yeah,
sharing.
yeah.
That answer my questions. Thank you so much.
Okay, thank you for me. Thank you. Okay, slideshow, run. So I think the question is coming from Hafi. Can you share your point on view regarding carbon emission or methane combustion of oil and gas industry? From drilling, refining to consumer is a concern of future generation. So actually, we have, you understand, Malaysia signed this Kyoto protocol that we should not have any more release of CO2 in the zone in the ozone itself by year 2050. So Petronas we start to think about going from different we call energy other than using fuel oil fuel. So that talking about oil and gas industry we more like dying off by year 2050. But in terms of the emission of CO2, but in terms of the emission of methane, we actually methane normally we can burn methane, and the byproducts of methane is almost like very negligible. But for CO2, it's difficult to burn, so we have still the carbon being released to the ozone, to the atmosphere, and it comes to causing the carbon the greenhouse effect, man. But for methane, normally methane is very combustible, and then it's very light. It start to go up to the top. Of course, methane also have effect to the greenhouse, but it's not as much as the carbon dioxide. So methane itself, normally to be able to reduce the impact, we normally we have the opportunity to burn and have the very less byproduct of methane. Because CO2 we cannot burn that easily. That's why it become a concern of releasing the carbon dioxide to the atmosphere. So in terms of drilling itself, whenever you have CO2, like in our case, Sabah Sarawak, there is a requirement, even the government request, even Petronas is pushing for all the oil operator to make sure that they process the CO2 and get the CO2 injected back to the reservoir as one of the gas injection. So CO2 will be injected to the formation. Or some cases where we have some processing where we can convert CO2 in terms of other byproduct, then normally we will bring along the CO2 to shore, and then from shore we pre-process and then make it a byproduct of certain thing that we can do with CO2. But of course, when we produce CO2 from offshore, it's so huge that it's going to be difficult to have the byproduct being used by the industry. There'll be a lot of research nowadays talking about how to use CO2, because we know that we're going to have more CO2 in the future before we can make it an economic project. Otherwise, your project will not be approved if you are not able to show how you're going to manage your CO2, from your field. Okay, thank you. So keep on writing, and at the same time, we're going to, I will try to answer most of the question again. So let's continue with our presentation. So then this subject on the generation of hydrocarbon, you can see this is the beginning. Or we don't know how hydrocarbon be generated. So we're talking about million of years ago. So we're talking about something that is beyond our imagination. But all that have been traced by the knowledge of geologists and geophysicists. And then, of course, all these expert on the plankton and so on. So hydrocarbon are primarily formed from organic material. Organic means that coming from the plant, from animals, and that's organic. Something that have component of carbon and each. So carbon and hydrogen actually is organic material. So the traces of the carbon have been found in meteorites, which suggest that they can be an organic material or hydrocarbon, or even some of the something came from from outside. So in other words, the most of the meteorites and so on come into to shore. Normally, they will carry some of the elements of hydrocarbon as well because of the carbon content. We call it the organic material. But some meteorites have a special material bioorganic that happen in the meteorite. So we try to differentiate between the two, something from origin of the oil, from the earth, or something from outside. So it is widely believed that geologists in the West world that commercial carbon are formed from organic material. But in our study research findings, it looks like most of hydrocarbon actually originate from organic material. I think we're going to discuss that as we go by. So you can see from the map on the right, the source of rock maturation. So how the rock is matured actually after millions of years, you can see that all this hydrocarbon generated by the source rock. The source rock is actually where all those plant and animal have been trapped to a certain area, and then what's been trapped is being accumulated. There's some sealing element on top of that at the rock, so there's no more interference from the top in terms of water or hydrogen or whatever, and then it will be sealed by itself. It's been trapped in one sealed area, and then once the Earth is moving out with all the tectonic movement, most of this accumulation of organic material will be buried down, deep down to the Earth. Sometimes some of the rock here is being buried down up to even 10 kilometers to 50 kilometers down the Earth. And then once being formed, heated up, processed over millions of years, and then the creation of oil and gas, which depends on the nature of your organic material. Then of course you can see from that zone, for example, in 55 kilometers or 10 kilometers zone, with another tectonic movement, it will lift up those hydrocarbon zone or the source rock to the shallow zone, and then from that region, because of the crack of the well of the earth itself, the hydrocarbon being trapped or being formed will be tried to migrate up. But based on the graph on the right side, you can see that as you go deeper, you have to have higher pressure, higher temperature, and then you have to see that most of the area is called kitchen for gas. So gas start to form. Even though you have oil will be converted to gas because of the temperature. And it go lower and lower temperature at the shallower depth, about 5,000 meter or 4,000 meter and above, then you can see the oil itself. So that's why in the oil and gas industry, we can say that once you go beyond certain depth, for example, in Malaysia, the moment you go below 3,500 meter, TVD, true vertical depth, you should see gas, no oil. So that's why when geologists recommend that, for example, they say that this might be oil at 3,500 meter, then of course we say that you have to check your numbers, because our temperature region in Malaysia is quite high compared to some other area like the American, the Gulf of Mexico, or even in Europe. So our temperature gradient is much higher. So that's why our oil is only discovered at the depth of 2,500 meter and above. It's very rare we see it at 3,000 meter. Below 3,000 meter, normally we see gas. That's why Sabah Sarawak, we discovered gas, huge gas at 4,000 meter, sometimes to 4,500 meter. So that more or less come up to the agreement that the graph is showing here, is that as we go deeper, and then you have high pressure, high temperature, normally you find gas. That's quite common. Like, of course, in some other country, some other region, they have a lower temperature gradient. Even though they have high temperature, but because of the temperature is low, you can still discover oil at a deeper depth. So it depends on the regional area itself. Okay. Then we go to the next one, biogenic generation. So you can see that millions of years ago, I think the Earth, our sea have some this planktons and zooplankton and so on. All these small microns are still being generated, they're being exaggerated. I mean, they've been built up, very fast. Like you can see when we talk about, for example, a bacteria, for example, the bacteria is expansion is so huge, from for example in 1 hour, from the virus, one bacteria, for example, it can generate millions of bacteria within 1 hour. The same thing like plankton. The expansion or the exaggeration of this plankton in terms of volume is going to be very high. So if the Earth is about 1 million years old, for example, just imagine that the plankton, the zooplankton will be huge. And because of course, I mean, the expiry after when they are dead, of course, they will try to bury it down with some of the organic material, and the development of this plankton continues, and all the accumulation start to increase more and more, and that is where the plankton will more be the source of organic material. It will be buried down and be pressed to one area, and it can complete compressions, and then will be buried by the sediment above, and then it be sealed off, and then it will start to be put into the kitchen, buried down by the tectonic movement or by the Earth's activity. Then you see that the source rock being developed, and the source rock have we create hydrocarbon, and then if no further tectonic happen, then all this rock becoming closer to the surface, and then start to migrate to the trap, and become the source of our oil and gas in the reservoir. Okay, so this plankton, even plankton seem to be very light, but we're talking about millions of years. The accumulation of this plankton is huge, that make it source of the organic material for hydrocarbon. Unique, very interesting subject. It's millions of years ago, not talking about 100 years, 1,000, no, it's about millions of years. Sometimes go to 500 million years in terms of the generation, including the dinosaurs time and so on. Okay. So this try to understand the geologic time. Geologic time is really related to the formation of hydrocarbon. You can see that from the graph, a million for years. How to read the graph? Do you see the 500 here is 500 years, 500 million years. It's 500 million years. This is the most activity that happened with all the planktons, the dinosaur, whatever happened to the Earth. This is the time, the era of Mesozoic, and then the Paleozoic, they call it. This is between the 500 million years ago. So we are on the Cenozoic, actually the time of the crust of the Earth. So we are here, and then we are talking about the Cenozoic formation, the Quaternary Tertiary. But seldom we see anything below here. You see even a small portion of the Mesozoic and the Paleozoic era, we can break down into further. Of course, the rest, if we talk about this Precambrian, is all very, very old. I think you're talking about most of the oil and gas. I think we neglect this. It's purely on education, understanding about the Earth. But most for hydrocarbon, we talk about the 500 million years ago with this era of Mesozoic and Paleozoic. And we can break down into further Cenozoic, Mesozoic, and so on. That is where most of the hydrocarbon will be happening. You can see that, like I mentioned to you, in terms of the depth. If those formation here happen in the range of about 5 kilometers deep, then the oil and gas is possible. When you go more than 4,000 meter deep, then you go to gas. So that's more or less some of the discovery of oil and gas in different era or the formation. So geologists have the ability to understand how to identify the age of the formation up to the tertiary. Normally our oil will be coming up to tertiary level, and gas, oil and gas. So this is where the plankton will be seen, and all this plankton will give the geologists and geophysicists the understanding about the age. So they know the origin of the hydrocarbon based on the age. So remember 500 million years, this is our time. The rest, too big up to 4,500 million is the very old. Maybe the core, the age of the or the latest rock in our Earth's crust. This is about 4 million plus. So I think we concentrate on 500 million, which is the subject we're going to cover more. Okay. Once we have geological time, we have the time scale itself. This is more on the 500 years. Talking about the 500 years, 500 million years, you can see where the plankton is happening, and then the dinosaur is also coming up in the years of 250 million. Or this is all the source of organic material that will be buried. So you can see that the first phase of the oil discovery is coming from the source rock coming up from the plankton. And then the later stage, you're talking about all the plant and the animals that become the source of the, of this hydrocarbon. So that's a different stage, different formation, and all this happening within millions of years ago, Like the dinosaur is between about 300 million years ago, up to 200 million is dinosaur time. But these millions of years, that is where the process is slow, but it's, talking about giving the benefits to the humankind later in our age. Okay, I think our age here mentioned about we are in the year about 1.8 million. So that's where we start to be, So Nabi Adam coming up to the world is 1.8 million years ago, something like that lah. For example, okay, how the formation of hydrocarbon. So process hydrocarbon, just to talk about how we bury the living organism, of course how the oil formation. So initially it called diagnosis. So diagnosis refers to the physical, chemical, and biological changes that occur in sediment after deposition and before the metamorphism. Metamorphism refers to temperature and pressure, the cooking itself lah. We're talking about the kitchen for this formation of hydrocarbon. It's called metamorphism. It's pressure and temperature reaction. So diagnosis actually happened before that activity of categorism, categogenesis. This is where the temperature pressure come in. So before that, you can see living organism will start to react based on the physical, chemical, and biological. Biologists start the turning effect. They start to destroy the structure of the organism and make it we call it the organic material itself for hydrocarbon. So once the first process happened, then because of the movement of the layers, it's being trapped as one reserve, one trap itself for the hydrocarbon. And then the cooking process we go through the process of earth movement and so on. If there's not much activity of earth movement, then sometimes the living organism will be stay there, and then there's not enough kitchen activity, heating process and pressure process that extract more oil from the organism unless you go to the categogenesis area. So this is where it's buried down there. And once the hydrocarbon form, and this as a source rock, and then you can start to travel to surface to the trap where we discover that through our drilling and our JNG study. So that's about diagnosis and categogenesis. We're talking about the organic material being converted to hydrocarbon at this stage. Otherwise, you still have only the organic material, but sometimes it can still be converted to gas because some heating process might also happen. So for some idea about the oil window, you can see that I've written here. For all window, when the temperature is within this range, 75 to 150 degrees C. See, so our boiling point is 100 Celsius. So it's more than 100 degrees Celsius, where the oil start to really be extracted from the organic material. But once you go below that, and you go higher, or temperature, 150 to 230, it's a gas window. So this is where some area will have deeper depth, you have still 150, so the oils can be found at deeper depth. In some area, the temperature is too high, you only find oil at a certain shallow depth. Then the rest is just gas reservoir that you can find. If it's too hot, then most of this hydrocarbon will be converted to graphite. It's become no value at all. It's been converted to the non-commercial value graphite for in certain depth. Okay, so that's the formation of hydrocarbon. Okay, so I think let me see to any more question if there's any. Any more question? I think the one answer. Thank you. Mana? Okay. I think there's nothing much. Okay, no question. Okay, let's go again. Okay, so migration and accumulation of hydrocarbon is another interesting topic. we're talking about the migration of hydrocarbon. So you see that when we have the source rock, this is the source rock where the organic material being trapped, and then the process of pressure and temperature that will extract some hydrocarbon from the organic material, and then we stored here, hydrocarbon, all this source rock. So all this source rock here is the origin of hydrocarbon. It will be there, and then it's nothing happens. So only then when we have a crack, then the source rock, the hydrocarbon from this area start to migrate up because most of the hydrocarbon is lighter. So it's try to find out a way up, going to the north because the density is light. So if anything, because we remember when you have process rock, you have the pressure, temperature, you have the energy. So it start to, whenever there's any release of pressure, release of crack, it start to go across the crack and try to travel up. So in this particular case, for example, there's one crack going up here, then you can see that it try to go in and try to fill up and move up to surface unless it being stopped by a cap rock, a sealing rock. So once you go there and then they cannot move anymore, and of course it will trap there, and of course after millions of years they will segregate because this is actually a combination of oil and gas in one phase. But now once being trapped, then the process of segregation, because temperature now getting less, pressure getting less, so the air, oil, and the gas will be separated from the oil and become a separation. But still there's some gas inside, but the free gas will be coming up as energy to hold every area in pressure, in a pressurized area. So when you drill this to the oil level, of course the oil with the energy will flow by itself to the surface. This is the example of reservoir rock, and then looking for a crack, then start to go and try to fill up your trap. Without a trap, without a seal, the gas, all the hydrocarbon will continue to go up to surface. So there's many evidence being found by the geologists, with some traces of hydrocarbon at the seabed, talking about all the potential leak that coming up millions of years ago. So that's why, what we believe is that most of the reservoir here or the source rock have been producing hydrocarbon, but if there's no trap, it will go to surface and lost in space. So more or less like that lah. So, but in most cases, when we have the layers of rock, we have still some good low probability sand, low probability shale. So that is what become a trap by itself. So this is a decline. This is the normal fault. That is the thrust fault area. It's all the type of trap that will stop the migration of the hydrocarbon from the source rock to surface. So this is what we want, and this is what geologists have been looking for in their seismic survey, in their study, looking for potential trap, and then to confirm there's a gas or oil, we drill a well. We drill a well to confirm the prediction from the geologists. And then normally, by experience, I think we know that they want me to hit the oil. So when we hit the oil, we just want to know how big is the reserve. This will be a case. Same thing like this, we always go. And most of the reserve, the thrust fault, normally we have quite a big reservoir area. And this anticline is another area, another trap that produces quite a big amount of reserve compared to other faults. Okay, so let me see. Then we have the sedimentary rock. So of course, once we have all the trap, whatever, I think the trap itself must be a storage quality, because with the storage quality, then of course we we have the gas that can go and trap there. Because if there's no reservoir quality, then of course the gas cannot be there. For example, some of the reservoir rock can have only about, for example, 10% of the rock area for white, for oil to come in. So 10%, for example, you have 1,000 barrel, I would say 1,000 barrel of rock, but you have only 10% of that rock can accept liquid or your oil. So it's only about 100 barrel, so it's not much. So the sedimentary rock might be able to have some white spaces for the oil to come in and become capped or reserved in that area. So you can see that sedimentary rock actually have quite high porosity compared to other rock. That's why it become one of the main component of hydrocarbon reservoir. So for geologists, they try to look into this kind of sedimentary rock, where they know that if the hypothesis or the correlation of the lithology showing that there's a potential sedimentary rock in certain depth, then they believe there will be a source on the reservoir that can keep most of the oil from the source rock, to be kept there for us to explore and to make it economical to produce. So you can see the sedimentary rocks, there's so many here. We can see even shale considered sedimentary rock, and shale have some fraction. Even you can see some shale oil, for example, in US, in Canada, they have shale oil where in shale there's a crack, and even it's a micro. Like for example, the shale have a crack or a porosity of maybe just about 5% or 3%. But if it is big enough, then even the shale might contain some of the trapped oil that been coming up from the source rock and been trapped there. So that's why normally in US or Canada, they use vertical well to drill through shale, and then they frack, so that most of the trapped oil between that shale will be more going through the conduit and produced to surface. So shale oil become a big surprise, that by having horizontal well, we can produce oil. If we go vertical, then the amount of exposure of shale with low porosity is not going to produce more. Unless you go vertical, horizontal, and then you frack, then you manage to extract the oil from the shale. Because the shale volume in Canada and in US is so thick, it can go up to 10 kilometers, 10 kilometers thick, in certain areas. So a majority, the high quality is about the 1 kilometer, 1,000 meter thick, where they can start to drill multiple horizontal wells and then fracture the area and produce this oil. Even it's small, because the volume is big, it's still economical project, especially onshore, because this is shale oil is only onshore. Shale gas normally, because of the volume is not that much, so shale gas normally will not that interesting or economical, because the volume itself is not that big. So shale oil is actually the preferred project for those onshore. Okay. You have siltstone. Siltstone is more like a clay, but still the porosity is still there, maybe about 3%, 4%. And gray wax also same thing like clay element, so very low porosity. But once you have something like this, this is a combination of high porosity and low porosity, so a combination. So once you have communication, permeability, then become very suitable for as reservoir rock. But all this rock has a very low porosity, so not much of reserve that can be recovered unless you become very thick. But once you go to something on the sand side, for example, mudstone is no. So you have the sandstone like this. Sandstone have a higher porosity, so sandstone normally become a very interesting sedimentary rock that normally provide more spaces, like 10% to 15% porosity, to really hold the oil. Like even most of the, like I mentioned, 100 million barrel recovery from this sandstone that can become economic for the country. Okay, sedimentary rock. And then we have, let's just choose some example of surface. Of course, this is from surface, but at the bottom, you just put it down at the bottom. But this is what is coming up, because of tectonic movement, some of the rock being lifted up. So we can see that, for example, in Miri, you go to the Miri, there's some side in Baram Delta, this is some outcrop. Outcrop means that the formation is being linked from surface going down to the below the sea. So you can see the formation is about the same. So by looking at the outcrop at the surface, you can appreciate the layers that happen. So in Miri, we have the opportunity to see the outcrop. What is going to be similar. So we evaluate in Miri, we can evaluate the porosity of each sand, the sandstone, the mudstone, and so on. So which one is the cap rock, the ceiling, and where is the potential oil being trapped? Even in some area, you can see that they have these layers being created because of the wave, and then because of the position, the sand being captured in layers. So it's a high quality, low porosity, high porosity, and so on, based on the color of different wave, different cycle. So for example, this cycle here could be another 50 years, and this is another 100 years. It depends on the amount of accumulation that happened. So it's going to be quite a good accumulation before the hydrocarbon travel from the source rock to this zone to be trapped. So this one. Sedimentary rock has two major types, clastic and carbonate. So clastic is mostly like sand. Carbonate is a carbonate. Carbonate have actually what happened carbonate in Sabah and Sarawak, the formation of carbonate offshore have a special process where they created quite a huge porosity. So the gas discovery in Sabah and Sarawak in carbonate have proved to be quite a lot. They have talking about 3 trillion, 5 trillion of the carbon is in place. So it's quite a big discovery in Sabah and Sarawak because of that carbonate. Clastic normally is the area where we're talking about mostly oil recovery. Gas in clastic, because clastic is about 10 to 15% porosity, so not as big as carbonate. So in carbonate, sometimes it's very tight. But in the different formation, different timing, the leakage, we create a carbonate to have such a good porosity for a big reserve, like in Sabah Sarawak, it's also in Sumatra. Also, they have the carbonate zone, and even you can see that in some of the Kalimantan, South Kalimantan, Sulawesi area, they have carbonate zone where they have huge gas reserve. Yeah, somewhere in Sarawak, in Indonesia. Okay, sedimentary rock. So you can see all this surface that's showing us what is actually similar features downhole. This is Arizona. The layers of sand is so good. Even you can see that it's so fine sand, and the porosity permeability is very good. Porosity can be about 10-50%. Permeability is good. Like even some is called 1 dasi of the formation, which is very good. Sandstone can be even layers, and it's dirty sandstone, so you can have a lower porosity and lower permeability, but still you can become a reservoir for oil and gas. In Thailand is shale. So you can see the shale thickness here. So shale oil, shale gas normally is trying to be, if it's onshore, we try to see whether it's any potential. But because, like I think in Sarawak, they also discovered some of the shale oil, but because of the volume, it's not big enough, and then it's only remote area. So we think that it's not economical at this point of time, for us produce oil from shale in Sarawak. Still early stage. Batu cave is a carbonate. So you can see that the carbonate batu cave is a bit tight, but in some area you can see some void. So in other words, it ranges from a very low porosity to very high porosity. Example of the carbonate formation within batu cave. You can see example of that. Okay, so now basin. This is when we talk about the huge accumulation of sedimentary rock, it becomes a basin. Basin means that it can store up to 500 million barrel, can store up to even if gas can go to 6 trillion cubic feet of gas. So in other words, the bigger the area for storage, the bigger the possible reserve of the area. You can see that the basin can be created by the fault, because you have a big basin, and then the fault itself will provide the seal so that the gas or hydrocarbon will not be traveling up. Because if it is still in the same layer, normally it try to travel to horizontally and going up to whatever weak point within the earth. So this happened millions of years. So the more trap, then the hydrocarbon will stay there longer and longer until we tap it. But it is not much movement, or if there's a lot of leakage at the top, the gas, all the hydrocarbon will start to travel up and even lost to space in some of the cases. So that's why we're hoping that with the tectonic movement, most of the trap will be created, and the hydrocarbon will be trapped in the basin, which is huge. So in Malaysia, you can see that, for example, in Tapis and Seligi, they have close to almost like 800 million barrel of oil in place, or recovery, sorry. And then some of the area are talking about even 150 million barrel is good enough for us to create a project. Near to shore like Sabah and Sarawak, even the 20 million barrel is a good start for us to produce the field. That's how big the sedimentary rock can hold. Okay. And then just to get some idea about Malaysia. So you can see the sedimentary rock in Malaysia, we are very lucky. We have a lot. You can see that, For example, here that's why in Peninsular Malaysia we don't see most of the oil in the close to the shore. It's always far away. So the Malay Basin actually is a basin where we have a lot of sedimentary. The rest is just but the part of it. But the main Malay Basin where we have the ExxonMobil, all the field here, and even all oil companies try coming having some oil here. Penyu Basin actually is another basin close to Pahang. But Penyu Basin have a quite poor quality of sedimentary rock, so the storage of the hydrocarbon is not much. Some marginal field have been proposed in this area because it's close to shore and some is being running in lah. So some marginal field is there. Some oil but not much. West Latuna is another big field with gas, but this is the Indonesian side. So West Natuna have a CO2 up to 60%. So if you have big gas, carbonate area or this sedimentary rock, but the problem is always that the CO2 is too high not to make it economical. You need to process CO2 and then you have to really inject back. So a huge amount of CO2. Normally, most projects fail to come to economics because of the high CO2. And our basin here is mostly the oil, and outside here is mostly gas area. So we have some gas within the sand. So this is the Vietnam. This is Thailand. So we are sandwiched between the two countries, and we have the joint venture, agreement to develop some field across the disputed boundary lah. For Sabah Sarawak, you can see huge Sarawak Basin. We have Sabah Basin, a huge basin here. But of course, like I mentioned, it depends on the quality of the sedimentary rock, whether it can hold huge amount of oil or not. But you'll be surprised that when we go for KK, Murphy, now PTTEP, they discover a big reserve in deep water in KK. And of course, I think it's close to about 500 million barrel deep water. Then they become a very big project for Sabah. Then Gumul, which is another shale area, shale development, also have another big gas. This is oil, sorry, Gu is oil. And then it's going to be quite interesting to, they are developing that then, and the economics seem to be quite good for the deep water. In some area, we discover huge gas, in Sabah. I think Kambangan also very big, and then they have some other big gas also coming from PTTEP, Lang Lebah. Petronas is going to be the Kasawari or the big producer, but it always issue with CO2. I think Kasawari, Sabah Cagali project, they have about 20 to 30%. And PTTEP, the new block in Murphy, I think they have about 30% CO2. And of course, some other field like Kembangan, I think they have about 20% or 10%. So it's not, but still they have some impact on the commercial value of that reserve to be calculated, because they have to remove the CO2 and only the clean gas we consider the commercial in their calculation for economics. Okay, so that's about the sedimentary basin in Malaysia. So let's see. Okay, there's no chat. Any question? Just please go to the chat. Or you can just switch on your microphone, then you can start talking lah. So anyway, so we continue.
There is actually one question Pak Tip daripada Pang KS about Hulu Miri. Not sure what is it referred to, but probably some areas over there for
Which
with
one is
oil.
in the drawing? Ulu?
Yeah, because there's a chat the chat from Pang KS.
Mm-hmm.
Yeah,
This Soi Kang, you're talking which block? What the name? Basin.
I think the Mulu Miri must be
Hulu Kiri.
Mulu and Miri.
Mulu and Miri.
Yeah.
Is that the question? So Mulu actually is a big limestone, is a cave, Mulu cave. Of course, they also call the area, the basin in Mulu, but it's a carbonate zone lah. Carbonate, when it is buried down, it depends on the porosity. So what happened in Sabah? In Sarawak, there is a very complicated carbonate structure, and at surface, close to surface, I think above 1,000 meter and shallower, they call it karst. Karst is actually a big hole almost like a similar to the Mulu cave. So we found it very difficult to drill across this cast because the moment we touch the big hole, everything will be lost. So we don't have any control when we drill a well in the cast area. So that's why we are almost like have difficulties to explore below the cast. But with the technology of seismic, we should be able to map that cast and try to penetrate along, try to go deeper by avoiding that cast through our seismic processing. So nothing much. Okay, not to know. Any more question? Let me see. Uh, this is okay. That's on the chat. Mulu Miri. Mulu, okay, the Mulu Miri. So Mulu Miri, Mulu represent the, like I mentioned to you, the carbonate cave. And then we have the similar situation happen offshore, but not because offshore when we think about the formation buried, so most of the cave have been collapsed because of the burden from the top. So when we talk about 500 meter to 1,000 meter below the sea level, this is enough burden from the formation to really crush some of the structure of the cave underneath. But still, like I mentioned, we still have a formation, the limestone called cast, which is having some big holes as well, So about 500 meter to 1,000 meter. And it's difficult for even Shell before. Shell failed to drill this area because of that lost circulation across this huge carbonate, below the seabed. But with the technology now, you can see new company coming in, like the PTTEP, the Murphy. We discover all the gas and oil below that particular complex area. Once we know how to manage the cast, so that's the technology that coming in that help us to discover more oil. Okay. So just continue to ask question, then I try to answer that. Okay. So hydrocarbon reserve and sedimentary rock throughout the world. You can see that throughout the world, we have seen that sedimentary rock become main source. So like I mentioned, geologists we're always looking for sedimentary rock when they do the analysis, and that is where they confirm if there's any source rock, and once you have source rock that can happen because of the organic material combination, and then you can expect that oil migration to the reservoir in the sedimentary rock is going to be happening because the confidence is much better. And then, of course, you are going to drill a well, exploration well, to confirm the existence of the hydrocarbon. So you can see everywhere of this, in terms of the hydrocarbon, we check. You can see the offshore and onshore, of course, from the map, but it's everywhere. So you can see that the chances of hydrocarbon storage is everywhere in the world, especially I think like America. You can see America have quite a huge category of hydrocarbon, especially the Gulf of Mexico. Also with Venezuela, I think in like we know, Brazil discovered a huge deep water reserve. And of course, Argentina, Venezuela is the main product, one of the top producer of oil. I think they can. I think they're crossing to about 5 million barrel of oil per day from Venezuela. And Africa, of course, they are discovery from Nigeria side and so on. Okay, Saudi is different lah. Saudi is another big discovery. Okay, so petroleum products. This more or less like our last subject. So petroleum product, as you know, that when we produce the hydrocarbon, then the demand for hydrocarbon product is so, I mean, the hydrocarbon itself is huge because we can make a lot of things from petroleum. So petroleum derivatives can found in many items. So we can see whatever around you, there will always be coming from hydrocarbon. You touch your mouse, your computer mouse is plastic, so it's going to be your hydrocarbon. And then your mineral water is also from hydrocarbon. Asphalt is for tar road, the paint, the inks. Medical products, normally they try to use it because of, for example, they use like methane to make it more like feeling a coolness when you apply your medical system. Then of course you can still use some of the medical this petroleum product to make it feel a bit cooling, or some observant to make it even absorb to your skin and so on. And roofing shingles is a roofing for plastic, synthetic rubber, phone, television, and so on. I think it's everything lah. It's just a few. So all derivatives, you know that some are being processed. Some of the gas coming up from the oil will be more or less become natural gas. Like in Miri, when they process the oil in the Miri crude terminal, what are the remaining gas will be more processed, make it dry, and then they go to the community around the area, in Miri area. So I think in olden days, most of the Miri side they have the pipeline, gas pipeline for their cooking. So that's more contribution from the Shell lah. But even I think even in some of the project, whenever we have a gas, we try to rather than burning the gas, the methane, you put in a process make it drier and then put it as a bottle lah, and distribute around. Naphtha is mostly like a tar. It's used for road construction, and of course some other element like kerosene, the fuel, the power petrol or diesel will be there. Lubricant will be more refined. So by adding in more additives, they become lubricant for our engine. So you can see the application is huge. Okay, industry related to hydrocarbon. So you want to see what? So of course we want to go back. So for oil and gas production, you see the platform. If it is deep water, you see the compliant tower. It can go to about 800 meter of water depth. But normally, it's too high. It's not going to be that fragile, and it's not going to be that stable. In a very high seawater bed weather condition, this is not practical because it starts to swing a lot. In special Gulf of Persian, Gulf of even if it is any deep water in Gulf area, then less underwater current, then this compliant tower will happen. But once you go deeper to 1 kilometer, 2 kilometer water depth, or 3 kilometer water depth, you start to go with the different style. This style here. This you can see that for deep water, all this floating material, half will be for storage, another half will be for floating. So they will have a tension cable, and then you have your conduit to connect you to the reservoir, to the oil that is coming in from your set of we call it manifold. And then this design here is also a floating device. So in other words, there will be some storage. Storage may be normally at the bottom, and storage will be at the top, and then the floating will be at the bottom. So it will be tied in with the tension cables, and all this conduit for hydrocarbon will come from seabed up to surface, and there will be the processing plant here. So you can see that they drill a well with these facilities, and they produce with the same facilities. So they save the cost of building up the structure. This is another on shallow water depth, 800 meter or 1000 meter below. Because if it's too deep, then it start to be affected by the sea current. So it to be moved a lot. So this is normally having a big reservoir, shallow water depth, 500 meter, 800 meter. Then you can use it as your storage. There's no, but it's only to medium water depth, 500 meter and below. This is normal subsea facilities. If you want to have facilities, then of course you have the platform, but facilities mean you have all your oil from the subsea, but produced to the platform. This is for shallow water depth, 200 meter, for example. And this is all the fixed structure, within the 300, 500 meter more or less. You have 500 meter water depth, then the structure is not going to be too much. Otherwise, you need a lot of steel if it's too deep. And then that's why you convert back to your storage here, the tension cable, rather than using steel, using cable and float your facilities. So that's why it's all economics. Less metal, the better. And then you have all the drilling vessel, like you use semi-sub to drill a well in deep water. Anything beyond, let's say, 300 meter, you can use semi-sub. And of course, some of the semi-sub is for deep water up to 3 kilometer, and so on. Okay. So hydrocarbon fuel industry. So it's another fuel industry. Okay. Okay, let's see the one question. Check Bob. Okay, what is that? Okay, Fahmi. I believe FSO is the current emerging trend for oil and gas. Okay, production platform this day. What will you say? Actually, what happened when we talk about FPSO is a floating production and storage and offloading. So what happened actually, when you have a platform, the platform will have the processing facilities. So the FSO become FSO only storage and delivery. But because of the cost itself, normally what we want to do, the best approach, like you mentioned, is good. FPSO actually should be the trend in the future because FPSO remove the requirement of platform. But to have a FPSO, you need to have the well, subsea wells, and subsea wells normally require maintenance. So that's why in shallow water we try to avoid subsea wells so that we have platform to be able to to handle all the production and we go for the maintenance of the well comfortably with platform. But in deep water, because of the platform cost is going to be very high, then we have to really rely on the subsea wells, and this is where you're talking about how to manage the maintenance and so on. So this is more or less like understanding the situation of subsea well and FSO or platform and just the storage area. So, like I mentioned, if it is gas well, it's less maintenance. So gas well is quite convenient for us to go even for shallow water. Seabed well plus the FPSO for shallow water for gas because less maintenance. But if it is gas at the same time, you don't have FSO normally need big processing facility because you have to convert most of the gas to liquid, compressed. So it's going to be quite a big facilities. So normally when we talk about gas, we are always talking about pipeline rather than FPSO. So FPSO have that requirement, limitation, and of course it depends on the economics and of course the integrity of the well of the area. Okay, so I think we are almost to the end. Okay, after the hydrocarbon fuel, we have the gas industry. You can see the activities of gas industry is a lot. Gas, LNG bunker, also we have processing of that gas, LNG truck, and so on. It's most activity will involve with gas. And the transportation, the pipeline, of course, the gas for storage, the processing, and then production itself, the usage. This is the list from of the internet. Okay. Now, petrochemical is another area where hydrocarbon will be used, but petrochemical relate mostly to gas industry. So, like we mentioned, gas is a long change, so there's a lot of things that can be do by adding in some chemicals, some organ, some structuring of the carbon link. Then we can have a lot of material. The polymer plant also being interesting. The hydrogenation, the coker unit, CO2, gas refinery. You can see that the industry is huge with this. And then, like for example, we have in Latif, we have we have the gum plant, the chemical plant using gas. And in Bintulu, we have fertilizer plant. We have we call it base oil plant from Shell that using gas. So there's a lot now. Of course, at the same time in Bintulu, they are having the gas and then they compress the gas to become liquid and they export that by tankers, the liquid tankers to Taiwan, to Japan, and so on. So our gas industry is huge. And then I think we are I think we are maybe second or third from Dubai, from Kuwait. Okay, what can we manufacture from natural gas? I repeat again, mention this is a lot. Yeah, I think we have so many products coming in. Okay, in summary, you can see that natural gas, paraffin series, and then gas phase at room temperature, the crude oil. This is the series of paraffin, butylene, and so on. Liquid at the pressure, and then like oil, this is the range of API, heavy oil. Semi-solid, now we talk about the tar, the Canadian tar sand. This is solid viscous. And then it can also, like Canada, is a huge amount that can be making economical. So sedimentary rock are formed from deposition of sediment in the lake or ocean, sedimentary rock. Majority of the world hydrocarbon found in sedimentary rock. Geological time, time extending from the end of formation of Earth to the onset of human history. This is where geological time behind us, that the God created the opportunity for us to use hydrocarbon that have been developed million years ago. So most organic material that come in hydrocarbon were actually from plankton. So you'll be surprised. It's such a small creature, but the benefits they create to humankind is tremendous. Okay. Summary, another oil is formed between temperature, so you know that there's a range. So if you are in joining any company, okay, if you drill too deep, of course you got to find gas. But if the reservoir engineer saying that or the geologist saying that, okay, we found some potential hydrocarbon at temperature of 100 degrees C, for example, then most likely you say that it's going to be oil. Something like the general knowledge, understanding about the kitchen for formation of oil or the formation of natural gas. So millions of years, source rock, mostly shale and so-called the organic material buried and deformed. So organic fluid either squeeze or flow up from the fractures. That is the hydrocarbon itself will flow to surface because of the light the light density of the liquid. And then you have trap, it will be trapped. If otherwise, you go to lost in space lah, like I mentioned. So hydrocarbon travels upward through the fractures and fall until it reach the impermeable zone or lost to space lah. Hydrocarbon accumulates in the reservoir rock. So this is where currently everywhere in the world people are looking through this source rock and try to have a block in every country. For example, for Petronas we go to Suriname, we go to Mexico, just try to have a block, and we probably will explore the area. If there's any good potential, then we develop the field and it become the income for the nation. Okay. I think before any question, this last question, then I think we have another 3 minutes. So just type in what the question, then we try to discuss that.
Yeah, okay. So before we end, I think there's no more questions from the floor. Okay, yeah. All right, so thank you everybody, and thank you Pak Latif for an insightful session for the origin of hydrocarbon. We hope it gave the participants a clearer understanding of how hydrocarbons are formed and the geological processes that drive exploration and in the oil and gas industry. It's been a pleasure having your attention and participation. We look forward in seeing you in the next session. Thank you everyone. Bye bye. And do give us a feedback.